Okay, so we'll just talk about some facts about the functions. We discussed injective, surjective, all of these. I think all of the topics about functions uh, are related to these two properties as we went through this unit. And the last section of this unit is about some more facts about the functions. Again, we're talking about the injectivity and the subjectivity also. So the first thing we want to talk about the functions between finite sets. So that means a function f from set A to set B, either A or B is finite or both. And then for that case, we can talk about more interesting properties of functions. Okay, so the first theorem is about the image of the f, and this is pretty straightforward, I believe. So the theorem says let A and B be sets, and let f function from A to B if A is finite. So the domain is finite, then the size of the image of f is less than equal to the size of A. Okay, remember the two-body wall sandwich set means then the cardinality, the number of elements in the set. And the image of f includes all the elements in B in the codomain and that mapped from set A. So that's another set, a subset of B. So then we can talk about its size also, or cardinality. Moreover, so again, A is finite, F is injective if and only if the image of F has the same size as A. Okay. So this proof is pretty straight. Okay. So the first part, if A is finite, then the size of the image of the function is less than equal to the size of the domain. If you think a function as all the pairs, then the function has all the pairs of size A, right? Because each order pair corresponds to a element in set A. Okay. So then you have at most the size A second coordinates, right? Because each order pair has one second coordinate. So you have the size A elements or all the pairs. So then you have at most the same size of second coordinates. Sometimes you may have repeated second coordinates, then it will be less than the size A, right? But at most is the word in here. So there cannot be more than size A elements in the image of F, right? The second all coordinates in this function F, all the pairs is the image of F. Okay, so that's the first part. It's pretty easy to prove. And then we need to show that F is injective if and only if the image F and size A has the same has the same size as the domain A. So we need to prove in two ways because it's if and only if. So assume that F is injective, then we need to show that the size of the image of the function is the same as size of the domain of the function. You know, F is injective, that means all second coordinates of pairs in F are distinct, right? Each element in the domain of F maps to a distinct element in the codomain. So you're gonna have the same number of images or second coordinates as the same as the size of an image as the same of the size of the domain of the function. Okay, because it's one-to-one. Well, then you have to show if the size of the image of function is same as the size of the domain of function, then you have to show this function is injective. Okay, so we can prove this by contrapositivity. So then you just assume f is not injective, then we come to some contradiction. Okay. So if f is not injective, then f has fewer than the size of a distinct second coordinates. Because you have repeated second coordinate in all the pairs. All right. So then the image of the function is has a smaller size than the domain A. So that contradicts with the assumption of the image of f and the domain of f has the same size. I think it is pretty obvious. And the next theme says, again, we have a function f from A to B, and B are both sets. So this time, let's say if B is finite instead of A. Okay, the previous theme is about the size of A, finite. But this time we're talking about size B. B is finite, then what can we say is the image of a function of less than or equal to the size of B. Okay, the size of the image of f is less than size of B, and f is surjective if and only if the equality holds. The image of f equals the size of B, and this is pretty easy to prove actually. If B is finite, then you cannot have more elements of the image of the function. The image of the function is just part of the set B. So then obviously the number of elements in the image of a function will be less than or equal to the size of the column B. Well, if f is surjective, then well, all the elements in set B have three images. So I mean the image of f is just equal to set B. So the size, of course, they're the same because they're the same set. Okay. The next theme is also pretty straightforward. This time we talk about the A and B both finite. Okay, so that just extension of the previous two theorems where one is assume A is finite and the other is assume B is finite. So this time we assume A and B both finite. And again, f is from A to B, a function, then if f is injective, then size A will be less than or equal to size B. If f is surjective, then size A will be greater than or equal to size B. If f is bijective, then size A equal to size B. Okay. And these are very easy to see. You know, for example, if f is injective, then you got the same size of domain and the image because it's injective. So each element in the domain maps to a different element in set B. So then you get same size of the image as the domain. And you know, obviously the image of F will be a subset of B. It has to be the case by definition function. So the size of image of the function will be less than or equal to the size of B. So then you get the size of A less than is equal to size of B. And for the second part, if F is surjective, obviously, you know, the size of domain is always greater than or equal to the greater than or equal to the size of an image. You know, if you think about all the pairs, you know, you can have at most the same number of all the pairs as the number of elements in set A, right? But F is surjective, so the image of F is the same as the codomain. Okay, so the size are the same. So then you get the size of A greater than or equal to size B. And the part C is obvious from A to B, you know, because F is both injective and surjective. So then from 1 size A less than or equal to size B, and from 2 size A greater than or equal to size B. So the only case where these two are true at the same time is size A equal to size B. Okay, pretty straightforward. Okay, let's just look at some examples. Suppose we have two sets A and B. Set A has 4 numbers 1, 2, 3, 4, and set B has five numbers 1, 2, 3, 4, 5. Obviously, size A is less than size B. So then you know, there can be no surjective function from A to B. You can use the theorem on the previous page, but also, you know, this is obvious because a surjective function from A to B requires the image of A is the same as the set B, but B have more elements than A, and you can have at most 4 elements in the image of A, right? So that's impossible. So obviously there can be no bijection from A to B. You know, if there's no surjection from A to B, then of course there's no bijection from A to B. All right. There's a very interesting property here, which is also interesting. When the size of A and B are equal, you know, of course we assume they are both finite, then injectivity and surjectivity will be true at the same time or imply each other. So the function f from A to B is injective if and only if it is injective. It's surjective. Okay, this is easy to prove. So we need to prove two ways. So one way, suppose you know, F is injective, then we have to show F is also surjective. So we just prove by contrapositivity that assume F is not surjective. Then the image of F will be a subset of strictly a subset of B because it's not surjective. So the image of F will be less than set B. So the size of image F will be less than size of B, but the size of B and A are the same. So then the image then the image of F will be less than size of A, right? So F is not injective, the image of the function is less than the size of the domain. That means there are some elements in the domain mapping to the same element or elements inside the B. Okay. So that's contradiction. So that means F has to be surjective. And then the reverse, then we have to show, when assume that F is surjective, then we have to show F is injective. Okay. That's also easy because just do it by contrapositivity again. And suppose F is not injective, then the image of F has a smaller size than the domain A, of course, right? Not injective. So there's some elements in the domain mapping to same elements in the codomain, so that the image of the function will be strictly a subset of the size of image function will be less than size of the domain. Okay, but size A is the same as size B, so then we get the image of F has the smaller size than size B, so F is not surjective. Okay, so then we get the conclusion that the number of elements in the image of F is less than the number of sets B. Okay, so F is not surjective. Okay, because when it's surjective, then image of F and set B are the same. Okay, so they're the same size. So we got another contradiction that F is not surjective. So this proves that the F has to be injective. Okay. I think this is pretty easy to understand. Okay. But the one thing to be careful is, we're talking about finite sets. The function defined between finite sets, either one or two, A or B or both. But when both are infinite sets, then all the conclusions do not hold. All the theorems are not true. So I actually you don't know what it means by the size of infinite sets. That doesn't make sense. But even if you have the two sets A and B are equal there, and they are all infinite. So suppose the domain and the codomain of a function are the same, and there are infinite sets. And then you can find some counter examples to show that the previous conclusions do not hold. So, for example, if we define a function f from the set of natural numbers to itself by this formula f of n equal to n plus 1, and define that function g between the same sets by this formula piecewise defined, So G is equal to 1 if n equals 1, and G is equal to -1 if n is greater than 1. Okay. So for the first case, for the first function, you can see f is injective, obviously. If you take a different number, natural number n, and then the function value will be also different. So that is injective or one-to-one, but it's not surjective because if you think about the number 1 in the codomain, the natural numbers, right? 1 is the natural number, so you cannot find the pre-image for f in the domain, because the only way that you get 1 is equal to 0, but that's not the natural number. So it's not subjective. It's not subjective. There's one in the codomain does not have a pre-image in the domain. And if you look at function g, then you will find out that g is subjective but not injective. Okay. G is subjective because because the image of G is same as the codomain, and so you get 1 taken into account in the codomain, and then if you just pick up any other natural numbers, then when n is greater than 1, then you get all the natural numbers from -1, right? So it is subjective, but it's not injective because when n is 1, you get a g equals 1, and when n is 2, use the second formula, you get 2 minus 1, which is 1. 2 greater than 1. So you get the same image for n equal to 1 and equal to 2. So it's not injective. So everything becomes very different when you talk about the finite sets and infinite sets. This is true not for a function, but for a lot of things. You cannot easily generalize the case of finite sets to infinite sets. You have to be very careful about that. Any questions about it? I think it's pretty easy. Okay, so just let's look at some more examples. Okay, there's one common use of the theorem 27.5. The theorem says when a function from f from a to b is injective if and only if it is surjective when the size of domain and size of codomain are equal. Okay, so that's the theorem. So if you just let function f from a to the cell, obviously the size of domain and codomain are the same, then you can use that theorem. So f is injective if and if f is surjective. Okay, so if you look at this example, 27.8, set A is the set of three numbers 1, 2, 3. So the question is, if the function from f from a to a is a function, is it automatically bijective? Of course not. You can have any kind of function from a to a. It doesn't have to be bijective, but if it is injected, then it is automatically surjective, and vice versa. Because domain and codomain are the same size, or actually they're the same. So, for example, if I say if this function is injective, then it has to map 1, 2, 3 to different numbers. So then you're going to get 3 numbers in the image. So that means that's the whole set away. So it is subjective. And if it's subjective, then if a to a is subjective, that means all the elements in the codomain with 3 elements are mapped from some elements from set A, and that only happens when the function itself is injective, because the domain A only has 3 numbers, so you have the same number. Domain and codomain, or image actually, when it's surjective, right? So then it has to be 1-to-1. So that's that. So if you say this function, if you know this function is injective, then you know it's bijective. Or if you know this function is surjective, then you know it's bijective also, right? Okay, so that's the first topic. The next topic is about the partitions and the pasting functions. So in some cases, if you have a function from a set A to set B where the domain A is very large or complicated, to write one single formula for the definition, then you can split the domain A into multiple parts and define a function from each part to the codomain. And that's actually the piecewise defined functions we talked about before. So then the properties related to injectivity and surjectivity of piecewise functions can be done by, considering each piece, or case by case, although it's a little tedious sometimes. It's still not very difficult. All right. Let's just talk about the spatial piecewise defined function related to injectivity and surjectivity. Okay. So let's say we have 2 sets A and B, and we just partition both sets by n ports or into n ports. So P1, P2 up to Pn is a partition of A, and the Q1, Q2 up to Qn is partition of B. So if you still remember what it means by partition of set, it means you just divide the set into multiple parts. Each part is not empty. You cannot, talk about the empty set in partition. It doesn't make sense. And also, the unit of all these parts should be the same as the original set. All right. And the other thing is, there's no intersection, or it's empty between any 2 parts of this partition or subsets. All right. So now let's just say for each I, okay. So from 1 to n, you can define a function f of I, f sub I from pi to qi. So this pi and qi, these are just subsets of p and q respectively. You just define a specific function f sub I between these 2 specific subsets, and then you just combine all these functions fi's for each subset pair. P1 to Q1, you got F1, F sub 1, and from P2 to Q2 you get F sub 2, and so on. So then you get a bunch of functions from one subset of P from one subset of Q, and then you combine all of them to define the function. just take the union of all the f sub s. If you consider the function as all the pairs, then you got for each of these f sub s, then you get some other pairs. If you combine, put them together, you get another set of all the pairs. So that's the f. Then you define a function from the whole set A to the whole set B, right? You know, these are all the pairs from A to B, basically. Each of these pairs coming from some f sub I. So the first element will be coming from subset of P, which is from A, which is also from A, and second coordinate of the pair, or each pair comes from some other pairs from subset of Q, but also that's element of B also. So that makes sense. And obviously you just define the function f, evaluate A as the same as it is evaluated in the specific f sub I. Okay, so just take a look at the element of A coming from each part of this partition, and then you just evaluate it using the function defined, and the f sub I defined on that piece of A, or subset of A, right? So there's a name for this function. We call f the function obtained by pasting together the f sub I. So, okay, easy to understand. So let's just see one example about this pasting or partition functions. So we have set A, it has 10 numbers, 1 from 10, and set let's just partition A into 3 subsets. P1 has 3 numbers, 1, 2, 3. P2 has 4 numbers, 4, 5, 6, 7, and the P3 has 3 numbers, 8, 9, 10. So each of them is non-empty, and its union, of course, is equal to A, and P1, P2, P3 are disjoint piecewise, I mean pairwise. So this set of P1, P2, P3 is a partition of set A. Okay. And they do the similar thing for another set of B, which has 5 numbers, 1, 2, 3, 4, 5. And this partition into 3 sets also. Q1 has 3 numbers, 1, 2, 3. Q2 has one number, 4, and Q5 has only one number, 5. Again, if you union them, you get the set B, and none of them is empty, and there's no intersection between any of those Qs. So this set of Q1, Q2, Q3 is a partition of B also. And then you can just define, a function from each Pi to each Qi. Okay, for example, if we define F1 as F1x equal to x from P1 to Q1, and define f sub 2 from P2 to Q2 by F2 equal to 4, and define f sub 3 from P3 to Q3 by f sub 3 equal to 5. So the F2 and F3 are constant functions. And then you just put them together, or pasting together those f sub i's. We got the function f as a whole by this rule. Okay, so if x is in P1, then we take the function value as f sub 1x. Okay, right? P1. If x is in B2, then we just take the function value as f sub 2x. Okay. And if x is in P3, then we just take the function value as f sub 3. And the whole thing makes sense. But if you write down everything specifically, that means f of x equal to x. If x is in P1, because the definition of S of 1 and the f of x equal to 4 if x is in P2. Again, that's just definition of f sub 2, and the f equals 5 when x is in P3, where the definition of f sub 3 is exactly that. So we got a piecewise defined function, basically, and that's it. I think it's time to stop here today. Any questions? I think it's pretty straightforward.
It was pretty straightforward.
Yeah, it's nothing really complicated in this section, actually.
Yeah, that's simple.
Yeah,
It's like transit in a way.
yeah, it's much more straightforward